Okay, so our next speaker is Aran Mooney. He's from Woods Hole Oceanographic Institute, which is in Cape Cod, and he's going to be speaking about the sound of science using healthy soundscapes to restore reefs.
Great. Thanks, Andy. Thanks, everyone, for attending here. So you may not know, or you may not have thought about, or you may not have listened to coral reefs, but coral reefs are really rich with sound. So they can be a cacophony of snapping shrimp, a variety of fish, and marine mammal species even that are passing by. So I'll just see if I can play a sound here from Tektite Reef in the Virgin Islands. See if this will go. Maybe I need to play from over here. So you hear the whales, you hear the fish. The first sound was a fish, more fish, and the snapping shrimp up above. I'm not going to play this 30-second clip for you. But these reefs are really rich with sounds, right? So we've done studies and shown on the spectrogram they see here, for example, on the y-axis frequency, time on the x-axis, and different sounds, and maybe 100 to 150 different sounds per minute on healthy reefs. So these fish are really chattering a lot to each other. And as early as 2010, there's been studies that have shown that if you look at the overall sound level on a reef and you compare that to coral cover, there's an association. Basically, there's higher sound levels on these reefs. But this is a pretty coarse metric because also sound can come from waves and boats and other things like that. So in our lab, we've been kind of looking at more fine-scale ways to kind of basically assess the acoustic diversity of these reefs. So this is, again, another way to visualize the sound on the reef. On the y-axis is the acoustic power, essentially the sound energy, then frequency, and then kind of in front there is time. And what you really see here is the fish acoustic activity increases at dawn and dusk. So there's essentially these fish choruses that happen at dawn and dusk. And that magnitude or the amplitude or the volume, or essentially if you integrate those dawn and dusk periods and you compare that to midday or noon or midnight, one of the quieter periods, that's associated with the reef fish density or the reef fish diversity and the abundance. So on the y-axis here is the magnitude of fish, the dawn dusk chorus compared to fish density, as well as coral cover. And we've done this across multiple reefs in the Virgin Islands. Now, we also know that we can use those sounds for management, but animals are responding to these sounds. So the fish are using them to obviously call to each other, but we see the settlement stage, there's a variety of studies, including from our lab, that settlement stages of a broad range of fish families are attracted to these reef sounds. And we know that coral larvae show phonotaxis, basically moving towards those sounds, they'll orient and swim towards those sounds. But it was really unclear how that sound basically affects coral settlement. And so that was sort of the basis of the studies that I'll be talking to you today. So I'm going to talk to you about two different studies, basically trying to address how larvae may use sound to find appropriate habitat and for essentially rebuilding those reefs. And the first study was published in 2018, led by Ashley Lillis, who was a postdoc in my lab at that time, also working with Amy April. And it was looking at in situ exposures of natural reef sounds and how that may induce settlement. And then the second study is something that we just conducted this summer, looking at how acoustic playbacks, essentially playing back those sounds of those reefs, might increase coral sediment at a degraded reef site. So in the first study, and both these studies actually happened in the U.S. Virgin Islands National Park, where we've been, it's a relatively healthy site for the Caribbean, about 300 fish species, 50 hard coral species, numerous gorgonians and sponges, and we've been monitoring, essentially listening to those reefs since 2012, and I think that's the longest continuous monitoring of any coral reef acoustically in the world. And so we have a really understanding of what the diversity and the variation that's going on there. So in 2017, we started the study where we collected Porites, asteroides colonies, brooding coral, and we brought them back to the lab. We put them in flow-through aquaria, and we allowed them to spawn, and we collected those larvae. And we could divide those larvae into different groups. And then we put those larvae into cups, essentially, on different reefs. And so in these cups is basically filtered seawater. We remove the bacteria, filtered sterilized seawater, and a clay settlement tile that was pre-conditioned. And then some of these cups are essentially light. They're allowing natural light, but some of them we made dark. And they're essentially impermeable to the chemical cues that animals may use to find a reef, but they are essentially acoustically transparent. So they are permeable to sound. So they're not getting the chemical, but they are getting essentially the sound. And then we varied the light treatment. And we placed these different sets of cups on 3 different reefs, differing in habitat, essentially quality, meaning the abundance of fish and the coral cover on these different reefs. We monitored the sound field in that environment, and then we assessed these chambers essentially after 48 hours. The first reef that we looked at was Tektite Reef. That's a relatively healthy reef. It's basically filled with abundant fish sounds. The second reef that we put cups out there with larvae, it was a degraded reef, Cocoloba. It's actually lacking in fish sounds. And a sandy control site, so that doesn't have a lot of snapping shrimp or a lot of fish sounds. And I'm going to come back to why I keep saying fish sounds in a minute. When we measured essentially the larvae several days later, we found significantly greater settlement at the chambers of Tektite Reef, the reef that's of higher coral cover and fish diversity. So on the y-axis here, you basically see the number of settled larvae, and comparing at our healthy reef, which is in red, degraded reef, and our sandy control. And so here's Tektite, basically significantly more settlement. We found more settlement with this sort of acoustically transparent cups in both the light and the dark conditions. But the light had a little bit more settlement, but also essentially a little bit more variability as well. Acoustically, when we look at those reefs, so on the y-axis here again is basically acoustic power, essentially the sound level compared to frequencies. Tektite is essentially highest in its low frequency acoustic sound energy, and that low frequency essentially again is where the fish sounds are. So the fish are basically generating that low frequency acoustic energy. So they're different, significantly different in the low frequency fish band. So if you look at that red Tektite on the left, that's higher in the low frequencies, but the shrimp bands essentially, where the snapping shrimp are, there's no difference. So we think that animals are really responding to, the coral larvae are really responding to the fish sounds, not necessarily the abundant snapping shrimp that are out there. And we know from other studies, in our lab, but a lot of other labs as well, that low frequencies are are the sounds that a lot of other invertebrates, such as oyster larvae or cephalopods, that's the sounds that they detect, low frequencies. So again, we kind of wanted to take this knowledge, and we went back this summer, and we looked at a study, and this was conducted by a grad student in my lab, Nadege Uki. And the question was really kind of simple. Will the acoustic playback of a healthy sounding reef increase settlement at a degraded reef site? So we had 3 different reef sites again. This time we're using Salt Pond, which is a degraded reef site, but that's where we're going to essentially enhance the sound field. We have the negative control, Cocoloba again. So it's the same setup here. We put out a speaker, but that speaker is playing no sound essentially. And then we have a positive control site, and this is Tektite. And Tektite is again abundant and healthy, a lot of healthy fish sounds. And actually, we take those sounds from Tektite and we play them essentially on Salt Pond, so we can really directly compare those 2 sites. One of the key first steps in this is to kind of make a really robust system. So we had a prototype from a few years ago when we looked at some fish studies, but we kind of basically made a system that we think is kind of practical and transferable essentially. So it's lithium-ion batteries and a solar panel for extended use, so we can put them out there for days or weeks or probably much longer. We essentially never, we can check the battery level with our cell phone when we drive by it, and so it didn't really run out of battery. It did great. Is a programmable clock, so we can tell it when to turn on or turn off, when to turn the sound on or turn off. So we essentially would start the sound at 6 p.m. And then run all night and have it turn off at 6 a.m. And we're conservative in the beginning because we didn't know how our battery and how long our system would last. So we can control the amplitude or how loud the sound is as well. Basically, you control the sound files by essentially loading them onto a micro SD card on our computer and putting that into the board that we create. Already 3 minutes? Okay, 3 minutes till 12. And so then we would play those. We can basically make a custom board and custom code that was pretty updatable, a little user friendly. It's pretty manual or draft manual for us as well, and it's pretty cost effective. The most expensive part of that is the speaker. So we go out, we collected the Porites, Asteroides colonies. Again, we brought them back to the lab for spawning, and we're going to measure settlement in 2 ways. Again, similar to before, we have these cups with filtered seawater, but also settlement tiles out there. And so the settlement tiles are now dried, and we're looking at that data now. So we don't have that field settlement data yet, so I'll talk to you mostly about looking at the cup data, which was 3 days after essentially the sound treatment. So we let those cups out there for 3 days most of the time. We also looked at distance from the speaker here. So I'm going to play you one more sound file. This is essentially measuring the sound at 1 1 meter from the speaker here, and you're going to hear the first 6 seconds is what the reef sounds like without the enhancement, and then 6 seconds into this file, you're going to hear basically our sound enhancement turning on. Sorry, it's hard to drive and drive this. So pretty quiet. So there's the enhancement. There's fish sounds immediately, basically, when you start to play it. And this is basically just, just starting the sound at 6 p.m., Tektite sound starting at 6 p.m., and then playing it. Again, measuring the settlement at different distances. And so this is the data that we would see. So the y-axis here is number of settled larvae. Again, orange here is our salt pond, our enhanced site. Blue is Tektite, the healthy reef site that has essentially natural reef sounds, and gray is our sounds without any enhancement, or a reef without any enhancement. And we found a significantly more, and we did this both in June and July, essentially around the new moons, significantly more settlement with acoustic treatments, essentially, at both our sound and enhanced sites. We also kind of wanted to look at timing, right? And that has to do with a bit of the competency period for larvae, right? So Porites has a competency period. It's ready to settle about 3 hours after it's been spawned, but it goes for a very extended period of time. And so on the y-axis here is the settlement percentage on the y-axis, and then sampling the cups at 24, 48, and 72 hours after we started the sound enhancement. You can see there's always a difference between the enhanced and unenhanced site, orange and gray, with more settlement at the sound enhanced site. But again, it doesn't sort of, the timing was not in effect, and that kind of makes sense because these Porites are always kind of ready to settle. What about distance? Again, on the y-axis, number of larvae per cup that are settled, and then distance from the speaker, and then and you can see that basically it did drop off with distance up to about 30 meters, but when we compare to the other sites, we're still always higher than that sound enhanced site. So we didn't really reach the end of essentially our range of enhancement, at least at this site, Salt Pond. And then lastly, I kind of want to show you the second species here, and we did this again with Favia, another brooding coral, a field study and a tank study. So we have these cups in the field, but also cups and a quiet sound enhanced tank and a quiet tank in the lab. And the y-axis here, again, is number of larvae settled, and then we're comparing 24 hours of treatment in our sound, again, with orange, or our control or quiet sites in green. And what you see is a significantly more settlement, essentially, with Favia at 24 hours, but not more settlement at 48. And so what do we think is going on? Well, it seems to be working pretty well at 24 hours, but Favia has a much shorter competency period, so about 8 to 36 hours. So what we think is that they're choosy with that site early on, but by 48 hours, these guys are just desperate, and they're going to settle wherever they are and just simply pick a site or pick a tile. So what do we kind of think is going on here a little bit in summary? So we think, obviously the healthy coral habitat, you have an abundant fish community that makes a lot of sound, and that can help bring in settlement of coral larvae, which make that habitat. And of course, this is broken a little bit, and we're trying to kind of start or rebuild this cycle or circle of life, if you will, with the fish sounds. I haven't really talked about the fish data because we don't certainly experience with fish too. That's important. We can get some of this with fish too, kind of depends on the taxa. But we think that these sounds can play a potential role in at least some settlement. So where are we at this? Well, I kind of have this a little bit faded out here because I think there's ways we can always optimize the technology and build out to get to some of the more reef building corals or maybe soft corals. And we really want to collaborate with the folks like you and other practitioners. But I think we're at a place where we can start to kind of think about integrating this a little bit more into the field. And we're doing this a lot in coercion with the physical oceanography, trying to understand the currents of the system too, because basically these guys can move towards sound. They're swimmers, but they're not Olympic swimmers. So there's ways that we can kind of build, as you can see, into the local systems. And that's where we are. So any questions? Thanks very much.